Projectiles. As I said just before the break, a projectile is something that's been thrown. A cannonball is a projectile. A rocket is not. At least a frictionless projectile, which is what we're going to restrict our attention to here. A frictionless projectile is a freely falling object. So any sort of aircraft that gets thrust from its engines is not what we're talking about here. It's a cannonball or a baseball or something like that. Now, as I said, we're going to stick to the frictionless case simply because that's simple enough to deal with in a course at this level. If you're going to bring air friction into it, you have to have a course with a prerequisite of differential equations. So actually, we're talking about baseballs. We are not talking about artillery shells because they go at a couple times the speed of sound. And there is definitely significant air drag at that speed. On the other hand, people throwing a baseball around don't generally sit there and do a bunch of calculations before they throw the ball. That's more the kind of thing you would do with artillery. But, well, it's an introduction to the subject anyhow. And also, it's a good exercise in working with vectors, which is something that comes up over and over again throughout the study of physics. You get into electricity and magnetism in the spring semester. There's electric field vectors and magnetic field vectors. And so that's one of the reasons for covering inclined planes also. It's just a good exercise in learning how to work with vectors. So the way you deal with a frictionless projectile is it basically builds on what I covered in section 1. The way I usually like to explain it, like it says right here, is imagine you're in some very large dark room, okay? Some big arena where they might play hockey or the Rolling Stones might have a concert or something like that. And you decide to throw a ball. Well, imagine there's a spotlight way up there above you on the ceiling. When I talk about the X components of that ball's position, velocity, and acceleration, that's the position, velocity, and acceleration of the shadow of that ball on the floor. And when I talk about the Y components of the ball's position, velocity, and acceleration, well, imagine there's a big wall right behind you. And way off in the distance, there's another spotlight directly in front of you, okay? So aside from the shadow on the floor, there's also a shadow on the wall behind you. And you throw the ball, and that shadow goes up, and then later on the shadow comes back down, and the position, velocity, and acceleration of that shadow is what I mean by the Y components of the ball's motion. So, basic principles here. The shadow on the floor has a constant velocity. From the moment that it leaves your hand to the moment that the ball hits the floor, that shadow on the floor does not speed up, slow down, or change direction because there are no forces toward the front or the back. It's a freely falling object. The only, a little box just came up that said I might be a victim of software counterfeiting. I'm not actually worried. Let's just get rid of that. Okay. It's a freely falling object. Now, if you bring air drag into it, then the friction would have a component toward the back, okay? And as time went by, the shadow on the floor would gradually slow down. But as I said, we're going to leave that for a more advanced course than this one. In the frictionless case, either air drag is small enough to ignore, either that or you're firing artillery on the moon, one or the other. But since gravity pulls straight down, it has no component toward the front to make the ball speed up. It has no component toward the back to make the ball slow down. So the shadow on the floor just goes right along at a steady speed. The shadow on the wall behaves exactly the same way as if you had taken the ball and thrown it right straight up along the y-axis. That was the last example at the end of section 1. There was a ball or a rock or something, I forget, I'd have to look. Whatever it was, you threw it straight up, and a little while later it came right back down and hit you. And that's what the shadow on the wall behaves like, okay? The y component of, well, might as well write it out in detail. It only takes a moment. Oh, wait, we haven't gotten to Newton's second law yet. Well, for something you can look back at a couple of weeks from now, after I've done F equals ma, there's our projectile. There is the only force acting on it. As we will see in a week or two, mass times the gravitational acceleration equals the gravitational force on it, okay? Summation of the forces in the y direction is equal to m times a, because the x component of the acceleration is 0 because of the lack of any horizontal forces. mg is the only force acting, well, if up is positive, then this would actually be negative mg. And the masses cancel out, and the acceleration, the y component, maybe I should do it this way. Y component of the forces is what determines the y component of the acceleration. And so the y acceleration is the gravitational acceleration. And I really shouldn't have said that this week, but like I said, if you want to rerun this, I will get to Newton's second law soon, and that's what I was using there. Anyhow, whatever sort of justification you want to give for it, the y acceleration is equal to the gravitational acceleration straight down. So what you can do for, you know, if you throw something at an angle instead of straight up, and it goes along an arc sort of like that and hits the ground over here, is you go back to section 1. There was that group of equations for uniformly accelerated motion. You use them to write one equation for what's going on with that shadow on the floor. You use them to write another equation for what's going on with the shadow on the wall. And between those two equations, you can solve for the thing you're looking for. So that, excuse me, that's the basic background. Most of this is review from last week, just with this additional idea that you've got two components, and you have each one behaves independently of each other. What's going on in the x direction has no effect on what's going on in the y direction, and vice versa, because there's no forces at an angle or anything like that. So let me run through an example so you can see exactly what I'm talking about. So you've got a baseball or a tennis ball or something like that. You hit the tennis ball with your racket, and this is the speed that it leaves the racket with, and this is the direction that it's headed at that moment. And apparently the tennis court slopes somewhat uphill, because we're going to say it hits the ground at the same height that it bounced off the racket. So where does it come down? I mean, that's pretty much the typical question you're interested in, whether you're talking about firing artillery, you know, who exactly is it I'm going to blow up when I shoot this thing? Or if you're throwing a ball, you know, I want that guy over there to catch it. So where is this going to come down? So it goes like this. If you're going to write an equation for the x components, and you're going to write another equation for the y components, you need to know the components of everything. So we'll start with that. The question describes the initial velocity. The ball was thrown, here's the initial velocity. It was thrown with a speed of 37 meters, or no, 23 meters per second. And the direction at the moment it was thrown was 37 degrees above the horizontal. So just like the example I had you work on before the break, incidentally, if you're hearing various, I don't know if the microphone's going to pick this up or not, but if you're hearing various beeps and crashes and things in the background, I happen to be sitting about 15 feet from an active construction site. They bought the property next door, and they've got backhoes and all sorts of things. Yeah, they're over there busting up some concrete right now. Anyhow, just like the example I had you do before the break, this side of the triangle, the adjacent side, is the hypotenuse times the cosine. You use cosine to get the adjacent side because cosine is adjacent over hypotenuse. You use sine to get the opposite side because sine is opposite over hypotenuse. So this is, maybe I should label it, VI for initial velocity. VIX for the x component of the initial velocity. If one subscript is good, two must be twice as good, right? Hypotenuse times cosine equals the adjacent side of a triangle. You punch that up. Again, as I think I mentioned before, being sure your calculator is in degree mode, otherwise you're going to get something completely different. 18.4 meters per second. So at the moment the ball is thrown, that's how fast the shadow on the floor would be moving. Yep, 37 degrees. Hypotenuse times sine is the opposite side. And run your fingers over the calculator a few more times, and you've got 13.8. And actually, as is typical, these numbers keep on going. I've rounded them off to 3 significant figures. I kind of like to carry actually one more decimal place and then round off when I get to the end, but on the other hand, I don't like to make people copy all those additional numbers as I'm working through a problem. But anyhow, the question is, what is, maybe I'll draw a little sketch over here. So if there's the ground and you threw it over here, the ball goes up comes back down. And from there to there is a distance delta x. That is the thing we're looking for. Okay, how far away does it land? Well, delta x would equal this speed times the amount of time that it's in the air. Here, wait a second. Where's the... I got the formula sheet handy. No, of course not. Well, anyhow, if we go back, I can get it out of the note packet also. If we go back a little bit into section 1, one way of looking at it is right there. In the x direction, the velocity never changes. When the velocity never changes, the average is equal to the instantaneous at any moment. You know, you get a bunch of numbers that are all the same and average them. And, you know, if you've got 30 people sitting in a room and they're all 57 years old, the average age is 57. Add up all those 57s and divide them by 30, and what do you get? So when something never changes, you do not need to distinguish between the age of one person and the average of all of them. And when velocity never changes, you don't need to distinguish between average and the velocity at some instant. So average equals initial equals final equals the velocity at any other point. If this thing was going 13.8 meters per second when you first, you know, when the instant it left your hand, it's still going to be going 13.8 meters per second at the last instant before it hits the ground. So delta x, the thing the question asks me for, is equal to that 13.8 times the time. So if we only knew how much time the ball was in the air, well, we can figure that it's sort of a two-step process you have to go through. You can figure out the time by looking at the y components. Once you know the time, you stick it in here. We're going to get the y components out of this one. When you think about what I called x here, will be, I'll call it y when I actually start writing stuff down to distinguish, you know, the distance in the y direction from the distance in the x direction. We know everything in this one. If you're thinking about the shadow on the wall, we know everything in this one except for the time. And then once you get the time, you stick it in there. So that's the strategy. That's the plan of attack. That's not the pen I was using before. I don't know where I put the pen I was using. Oh, that's it right there. Black pen on a black desk. Okay. Shadow on the wall. Delta y. Take the equation I was just talking about and stick y subscripts all over it to indicate we're talking about the y components. The whole trick, well, it's not the whole trick, but one of the main things about working with vectors is to think in terms of components. Or let's say that's usually the approach anyhow. There are other ways of doing vector arithmetic, and once in a while one of them is a little more straightforward. I showed you the scale drawing method, for example, but the great majority of times you want to think of vectors in terms of components, okay? One of the most common examples, or one of the most common problems, examples of a problem, with a problem like this one, is like right here for the initial velocity. What you need to put in there is the 13.8. And where I see people go wrong on their quizzes and exams over and over again is they say, oh, I need the initial velocity. It was thrown at 23 meters per second, and they stick the 23 in there. You don't want to be talking about the initial velocity of the ball itself. You want to be talking about its shadow. Okay, so here's another thing that might be less than obvious to you. Delta y. Okay, delta x is the thing I'm looking for. Delta y is 0. This is just like that. I might still have the paper here I was writing on when I did the other recording. Unless I don't. No, I don't know what I did with it. That was a while ago. Anyhow, there was that last example right at the end of section 1, where you throw the ball up, straight up above you and it comes back down. And I explained then why delta x, or here I called it y, delta y is 0. It's because this displacement does not mean the total distance you covered. This means how far are you displaced from where you started? How far from where you ended up to where you started? So delta y means y final minus y initial. And y final equals y initial. Okay? The question says, and I quote, I've got to find the right question. Oh, I turned the page. That's my problem. Here we go. It lands at the same height it was thrown from. Okay? So if you picture a y-axis here, initial shadow on the wall, the initial position of the ball was here, it goes up, it comes back down. The final position of the ball is in the same place. Y final equals y initial, no net displacement, vertically. Initial velocity in the y direction, 13.8 times the t. As for the acceleration, all freely falling objects, whether they're going up, down, or sideways, or anywhere in between, have an acceleration of 9.8 meters per second straight down. Okay? Getting back to F equals ma again, which I really ought to cover one of these days. The direction of an object's acceleration is the same as the direction of the net force on it. That follows from Newton's second law. If the only force on an object is pulling straight down, then the direction it accelerates will also be straight down. So minus 9.8. And then a few lines of math that look very much like the math that I used solving the last problem in section 1. And as I said at the end of section 1, there are several, not only in this problem, in many cases, there's more than one way of winding your way through the math. But with this particular equation, I think some of the examples coming up will be a little different. But what seemed like the simplest thing to me is just divide through by t. Of course, the ultimate no-no in mathematics is to divide by 0. So it is worth pausing for a moment and saying to yourself, the time is not 0, because obviously it takes a non-zero amount of time for the ball to go up and come back down. So 0 divided by t is 0. 13.8t divided by t, the t over t cancels out. Half of 9.8 is 4.9. And when you divide this term by t, t squared divided by t would be t to the first power. And then finish it off. And looks like that comes out 2.82 seconds. Okay, we now know how much time the ball was in the air. We're actually getting there. So, having written one equation for the shadow on the wall, let's write another equation for the shadow on the ground, which is going to be just distance equals velocity times time. And there's actually a couple of ways of getting that. I mentioned one a few minutes ago. Another way to look at it that takes you to the same place is just keep thinking in terms of this equation here. Delta x equals v initial x times the time plus 1/2 ax times t squared. Same equation, just stick x's all over it now because we're talking about the x components. Delta x, the thing we're looking for. Well, let's take care of this part first of all. Let me emphasize again, you need to think in terms of components. People get to this point in a problem like this one and they say, oh, let's see, it's a free-falling object, so its acceleration is 9.8. The y component of its acceleration is 9.8. The acceleration vector, if you draw, if you represent it with an arrow, points straight down. The horizontal component of a vertical arrow is 0, okay? So don't just say, oh, acceleration is 9.8 and just throwing 9.8s indiscriminately everywhere. Think in terms of components. The x component of the acceleration is 0. So that whole term just goes away. Distance equals speed times time. The same relationship you would have gotten if your starting point was x equals v average times time. Either way you want to look at it, whatever you like best. For initial velocity, just repeating myself again, do not put in the 23, it's the initial velocity of the shadow, 18.4. And if I ask a question like that, I'm pretty sure somebody is still going to do that. Actually, let me fill in the time. 2.82 seconds. So meters per second times seconds equals meters. And the answer is 51.9. Something like 160 feet or something in that neighborhood. It's a pretty good throw. Actually, it's a really good throw. Okay. Turn the page. So what's left of section 2 is for you to do a whole bunch of examples, because what I have found is that if I just run through an example like this one, and then I turn around and look at the class and say, so do you have any questions? I just get all this silence. Everyone's just kind of looking at me like, oh, we're fine. We understood that. You can go on to the next thing. And then I say, okay, you do it. And all of a sudden it's like, so let's see if there's any questions. This one is kind of similar to this one. Once again, the ultimate thing it asks for by the time you get to the end of part B, it's asking for delta x. Okay, I've changed a few details, like this one, for example. With the ball in this question, it lands at the same elevation that it was thrown from. This one here, it lands 120 meters lower, okay? I kind of had some movie with Johnny Depp in it or something like that in mind when I wrote this question. That you've got the pirates down here in this ship, and you've got the Spanish fort up here on this cliff, and I'm not quite sure how pirates got to be good guys, but anyhow, they're shooting at the ship, and part A is just to help you set things up. Okay, when we were doing one-dimensional problems, I said, well, you should make a little list. What are you given? What are you looking for? And I kind of glossed over that sort of thing in this one. Maybe I shouldn't have, but I got a little more step-by-step-ish in this one here. So before you worry about solving the problem, let's get everything laid out. And when components are involved, I mean, you don't have to lay everything out in a table, but that's a nice way to do it. X components, Y components. When I run through it, I'm going to put the word find in the little box for the thing that we're supposed to find, and fill in numbers everywhere else. And then you see you just go down this column when you set up your equation for the X components, and you just go down this column when you set up your equation for the Y components. And that might help you avoid the thing that I was going on and on and on about, like putting 23 here when it should have been 13.8. So once you've got it all organized, what I usually do when there's actually other human beings in the room with me is I wait a little time, and then I go over part A so that everybody's got that all straightened out before they start trying to throw numbers at equations. And then I have you work for another 5 minutes or so, and or a little longer. I just kind of look around the room and see how many people seem to be working and how many people seem to be bored. And then I'll go over part B. And then actually number 5, I could have just called that part C because it's a continuation of the same problem, but it's asking for something else, so I gave it its own name. So instead of where does it come down, the question is how fast is the cannonball going when it comes down, because that, after all, is what determines how much damage it can do. And so after I've done this one, I'll pause a little longer, and then I'll go over that one. And then I wrote out another example here. This one is meant to sort of give you something to imitate, well, for part A, anyhow, of this last one at the bottom of the page. So anyhow, pause here, fill in the table, then I'll tell you if you got it right, and then we'll pause again. And now I'm back, as if I'd never really gone anywhere. So probably not enough room on the bottom of that page. Let's start another one. So we've got displacement, V initial, acceleration, well, first of all, how far from the base of the cliff does it hit the water? The way it's drawn here, the muzzle of the cannon, it looks like it's directly above the base of the cliff. So the horizontal distance traveled by the cannonball, that's going to be the thing we're after. The distance from the base of the cliff where it lands is what we're supposed to find. The distance that it goes, I should label this, the distance that it goes vertically, its vertical displacement, 120 meters downward. It ends up lower than it's. Now, as I said last week, section 1, it's your choice whether you say up is positive or down is positive. And there might actually be some advantages to saying down positive here, but, well, there's nothing wrong with doing it the conventional way either. So that's the way I did it anyhow. If you want to do it the other way around, go for it. So if up is positive and the ball is displaced downward, then we want negative 120 meters for its displacement. Velocity, well, that was in the previous example. I had to do the thing with the triangle and the sines and cosines because it was thrown at an angle. Things are a little bit simpler this time. The velocity vector looks like that. At the instant it was thrown, that was the speed and the direction. So, the arrow points right along the x-axis, or it would if I had drawn the x-axis. And if you just can't resist a formula, go ahead and punch up the sine and cosine of 0 degrees. But you're going to find that 100 times the cosine of 0 is 100, and 100 times the sine of 0 is 0. It seems simpler to me just to say, what if there was an ant crawling across the page here, and it wanted to get from the one end of the arrow to the other? How far does the ant have to go in the x direction? How far does the ant have to go in the y direction? Well, if it starts at the tail of the arrow, our little six-legged friend is going to have to march 100 units in the x direction. So that's the x component. And then when it gets here, to get to the tip of the arrow, it has to turn left and move a distance of 0 because it's already there. Okay, so since it's right on the x-axis, it's already, dead horizontal. It is its own x component and has a y component of 0. And it's kind of a similar story for the acceleration vector. The acceleration vector looks like this. So this time it's exactly vertical. The horizontal component of a vertical vector is 0. And its y component is going to be 9.8 downward. Because I made this choice over here, it has to have a minus sign. So here's where you pause it again This was part A. When you come back, I'll go over part B. And now I do part B. So, imitating the way I did that other one, we're going to start out by finding how much time the cannonball is in the air. And then once you know that, you can get delta x from knowing the time. So to get the y components, if it's, here's the picture again, if it happens to be right at sunset, so that the sun is over here, you're going to get a shadow for the cannonball coming down the cliff, and that's going to behave exactly like a free-falling object. If there was a guy standing right next to the cannon holding the next cannonball, when the cannon goes off, it startles him and he drops the cannonball that he's holding at exactly the same moment that this one comes out of the cannon. The two cannon, to the extent it's frictionless, and we have this is a really low speed for artillery, but it is supposed to be the year 1512 or something like that. So, probably in 1512 even, they went faster than that. But anyhow, to the extent it's frictionless, the two are going to stay right at the same level all the way down and reach the water at the same time. So delta y equals v initial y component times t plus 1/2 ay times t squared. Take all your numbers out of here, and I suppose if you wanted to write it in, you've got all these three pieces of given information, and we're going to try and find the time. Displacement, 120 downward. V initial, 0. 0 times t is still 0, so I'm not going to bother to write the times t part. Acceleration, negative 9.8. And if you multiply through by -1, that minus sign cancels that minus sign. If we had said down was positive, then there wouldn't have been any minus signs in the first place, which is a rather minor advantage to doing it the other way around. But you end up in the same place. The minus signs cancel each other anyhow. So 120 equals 4.9 t squared. So the math is a little different than it was in the previous problem. And in the other one, this was 0, and you had a number here. Now this one is 0, and you've got a number over here. So instead of dividing, if you divide this through by t, it's just going to make a mess. What you want to do instead is this, 120 over 4.9. Oh, that's t squared. Beware of typographical errors. So that's equal to something. I don't really care what that's equal to. What I want to know is its square root. So to get the square off the t, take the square root of both sides. So divide and then press your square root button, and 4.95 seconds. Time it was in the air. Then delta x, v initial x times t, just like it was in the previous problem. V initial x is 100. So we're in that column now. Now I've got the 4.95. That's the answer. Now you pause again. Work on number 5. Well, if you're completely stuck on number 5 and you came back hoping I would tell you how to do it, I'll get to that eventually, but let's see if I can just throw you a hint and maybe give you one more chance to get there on your own. So as the cannonball reaches the water, it's going to be traveling in a direction, something sort of like that maybe. V final velocity. And that final velocity, like any self-respecting vector, has both x and y components that would, well, sometimes a component is 0, like these were here, but if you include 0, vectors always have both x and y components. So v final y, v final x. And what the question is asking for is this hypotenuse, the magnitude of the velocity. Okay, how long is the velocity vector at the moment it hits the water? It's asking for this. So what you need to do is you need to figure out what's this side of the triangle. You need to figure out what's that side of the triangle. Once you know both of them, Pythagorean theorem. So I'm going to ask you to pause it again and see if that gives you the nudge you need. And now I'm back to finish this off in case it did not give you the nudge you needed. On the other hand, of course, if this is all just painfully obvious to you, that's what the fast forward thing is for. You just get that little scroll thing on the bottom and nudge it ahead. And for the x component, a frictionless projectile maintains a constant speed in the x direction. So if it was going 100 meters per second to begin with, it's still going 100 meters per second in the end. V final x equals v initial x equals the x component it has everywhere in between, 100 meters per second. In the y direction, well, go back to this column here and use it to pick out an equation where you can solve for v final. And there's actually more than one possibility with the, let's see, yeah, with the information we have here, because we not only have the 3 things in this column, we know the time also. So that gives us several options for how to calculate v final. The one that I used is v final equals v initial plus at. Another possibility is you could use v final squared equals v initial squared plus 2a delta x. Filling in the numbers. in the y direction. V initial is 0. Acceleration, 9.8 downward. I'm kind of off the bottom of the screen, aren't I? And we know the time, 4.95 seconds. So that's how fast it's dropping, while at the same time it's moving horizontally at that speed at the moment that it reaches the water. Okay, so we've got our two components. V final equals square root 100 squared plus negative 48.5. Of course, writing down the minus sign was a complete waste of time because it squares away. A minus times a minus is a plus. So I could just have written 48.5 and not bothered with the minus sign. But if I did that every now and then, there'd be somebody that would say, what happened to the minus sign? So I figured I'd tell you. So as this cannonball dramatically tears through the sails of Johnny Depp's ship, but does not quite sink it, it's going 111 meters per second. The Paris gun, used by the Germans near the end of World War I. A very impressive piece of artillery. This thing was throwing shells at something like 5 times the speed of sound. They were actually almost getting these things into space because, you know, their forward positions were still quite a few miles from Paris. And you know, if you're interested in this kind of thing, it's worth Googling Paris guns. When you see a picture of it, it actually kind of looks like half of a suspension bridge, because, you know, if you just had the barrel of a cannon, like, you know, you're picturing some little short cannon that they were using during the Civil War or something like that. Well, you know, this thing did not have a barrel that was like 10 feet long or something like that, you know, that Robert E. Lee would be hauling around. This thing had a barrel that was long enough that it would droop under its own weight without some sort of support. So they had a suspension system of cables that looks kind of like part of a suspension bridge. Well, of course, this wasn't some modern cruise missile where you could be really precise with your targeting. They really had very little control over where the shells would come down. I mean, they knew it was going to be somewhere in Paris. The thing didn't really have a lot of military value because you couldn't say, well, there's a target over here that's important to the enemy, and I'm going to blow it up. You try something like that, it probably comes down half a mile from there. It was mostly a psychological weapon. These, you know, like I said, these things are going something like 5 times the speed of sound. So you couldn't hear it coming. The shell got there before any noises it might make. And so you'd just be walking down the street in Paris one day, and a block and a half in front of you, there'd be a car parked on the side of the road. And all of a sudden, without any warning whatsoever, blam, it just blows up. Anyhow, we've got the muzzle velocity. 45 degrees is what gives you the maximum range. Obviously, if you point a gun straight up, that's a really bad idea, because if there isn't a crosswind or something, the shell's going to just come right back down and blow up the gun that fired it. Also, if you fire it horizontally, you know, it's only got a couple of feet to drop to the ground, and it's not going to go very far. Halfway in between is where you get the maximum range. Tilt the gun at 45 degrees. we want the maximum height. I was saying these things were reaching the edge of space, um, almost 41 miles above the ground. So, I mean, that's not quite space, but you wouldn't want to try and breathe up there. Anyhow, what do we start out knowing? Well, maximum height, that's the distance that it goes in the y direction. So let's start out considering the y components. If we need to get involved with the x components, like to figure out the time again, well, we'll get to that when we get to that. But since the answer is going to come from the y equation, why not start out by writing down the y equation and seeing where we get? So the initial velocity, 1,600 meters per second at 45 degrees. And this would be the y component. The x component, I didn't bother to write down because it turns out we're not going to need it. We're considering it to be a freely falling object, which, as I said, for something going that fast is not quite true, but this will give us an approximation anyhow, a fairly good approximation, because half of the Earth's atmosphere by mass is within 3 miles of sea level. So if this thing's going up over 40 miles, pretty quickly it is going to reach an altitude where air drag gets quite small. And if you imagine, here, get my little sketch from the previous page back. If you imagine a really, really tall wall behind this projectile, somebody built a wall 41 miles tall, good luck with that. And the sun is on the horizon over here. The shadow, after you fire the shell, its shadow is going to go up slower and slower and slower. And when it reaches its maximum height, the velocity of that shadow passes through 0. Well, let's stop watching it at that moment. When it's at its maximum height, what's delta y at that moment? Okay, so if when it tops out is when you're going to end watching it, then the final velocity is 0. Okay, if you keep watching it after that, it starts getting a negative velocity as it comes back down. But if you're going to watch it from when it's fired to when it tops out, the velocity in the y direction is 0. Free falling object, find delta y. And you get out your formula sheet and you hunt around through the equations for unit 1, or for uniformly accelerated motion back there in unit 1. And you find this one. The way it's written there in section 1, it says v final squared equals v initial squared plus 2a delta x. Stick y's all over it because you're talking about the y components. Fill in these numbers, do the math, and you get the answer. This one here, part A at least, is asking you to do pretty much the same thing with a football. The question once again is, what is the height? The thing has been kicked in such a way it reaches its maximum height just as it gets to the goal. So the question is, does it go over the top of the bar and you've won the Super Bowl, or does it pass underneath the bar and you will go down in history forever as the kicker who lost the Super Bowl? So as you can see, peeking ahead at the answer, unfortunately, it's a lifetime of shame that's ahead of you. But to calculate the maximum height for this football, it's just going to be exactly this all over again. And then what is its speed at this time? That's going to be kind of like number 5 back here was. So pause it again, And now I'm back. Okay, number 6. I'm going to start that out the way I started out the first example I did about projectiles. Since the thing was thrown at an angle, maybe I should use the word kicked in this case, good place to start is getting the components of the initial velocity. I mean, maybe I don't have to do that absolutely first, but it isn't going to be long before I need to do this. Let's get it taken care of. So it was kicked at 15 meters per second and at an angle of 30 degrees. Should have kicked it a little higher. So the y component of that, hypotenuse times sine, is the opposite side. 15 sine of 30. And actually, I'm going to do the x component also. I'm going to need that when I get to part B. So while I'm doing this, I'll do it all. Caught myself at the last minute there. 15 times the cosine. Looks like that comes out around 13. Okay. So to answer part A, that is pretty much a rerun of that problem about the Paris gun. When it reaches its maximum height, at that moment, the ball is neither rising or falling. The y component of its velocity is 0. Initially in the y direction, 7.5. And then a couple lines of math. 56.25. I hate rounding off 5s. They're right in the middle. I never know whether to go up or down with them. So I'd usually just leave the 5 there. So a few lines of elementary algebra, you add that to both sides, and then divide both sides by the 19.6. And that's 2.87. But the way the question is phrased, it doesn't actually ask for the distance. It just asks for over versus under. Well, this is under. So that would be the answer there. But if I put a question like this on a test, there's probably going to be something that says, because, you know, over or under, it's a 50-50 shot. If you're sitting there flipping a coin, you might get full credit if I didn't slip in something that said, show me how you got your answer. The correct answer by itself will not get full credit unless you explain to me how. you know, that you weren't flipping coins or something. Part B, the speed of the football as it reaches its maximum height. Well, there's the parabolic arc that the football is moving along. And when it's here, it has some velocity whose x component is 13 meters per second. And for that matter, over here on the way down, it has some velocity whose x component is 13 meters per second. And when it's right here at the top, where its velocity is exactly horizontal, it has an x component which is 13 meters per second. But at that moment, it has no y component at all. I mean, if you want to think of it in terms of the Pythagorean theorem, like this other example back here, if this is equal to 0, then v final equals, you know, square root of the thing squared. The square and the square root cancel each other. V final equals v final x. If this, well, we're not talking about final in this case. We're talking about partway through its flight, but same principle in that if the x component is 0, the velocity is just equal to the y component. And so there really isn't any formula to fling around. It's just, well, aside from calculating the component, 13.0 meters per second is how fast it's going as it passes over the top. And the next page says Newton's second law. So in the next recording, I'm going to finally get around to that thing that I was prematurely flinging around today.